Welcome. In this video, we will take a look at the derivative rules, and we are starting in chapter 2.5 here. We're going to look at the definition of the derivative briefly here, and then we'll jump into the derivative rules. So as we see on our page here, we're kind of redefining here things we've taken a look at in our previous class with the definition of the general derivative f prime of x, and we have the derivative of a value at a point, or a function at a single point a. So we're going to try to use both of these. And the first question we'll go ahead and try to tackle is finding the general derivative of the function f of x is equal to 3x minus 2. And then we'll use the definition of the derivative to do that, and then we will try to find f prime of 5. So let's consider using that definition. We're going to start with, again, f prime of x is equal to, this is the limit as h goes to 0. And the first item that we need to really find in this limit is, what is f of x plus h? So we're going to do a little side work here and try to figure out what is f of x plus h. That's the first item that's in that limit equation. And so we'll do that with evaluating our current function, 3x minus 2 with x plus h. And we'll try to simplify this as much as possible. So we'll do some distribution. To find our f of x plus h. And again, that's the first item that we're going to place in our limit with the definition. So we can see that definition up top right here. And so we're filling in there the f of x plus h in the numerator. I'm going to take this and I'm going to be subtracting the function f of x. That's the given function. Call that 3x minus 2. And then divide everything by that quantity h. Again, h is the quantity that we're taking the limit of. We're taking the limit of the function as h goes to 0, or this distance between our points gets closer and closer and closer together. So right off the bat, we see some ways we can start to simplify here. We have a 3x and a minus 2, and we're subtracting both of those items here on the right side. So if I subtract both of those terms, this limit will actually end up with just a 3h in the numerator when I subtract those. So I can rewrite this limit as h goes to 0 of 3h divided by h. And then finally, we could just cancel out those h's. H in the numerator and the denominator can be canceled out to 1. And we'll be left with this limit as h goes to 0 is 3. And so the constant here, 3, as I take the limit as h goes to 0, that is not affected. This is still a constant value. We just call that 3. So this just told us the conclusion here that the derivative f prime of x is constant at 3. So this has a constant derivative. This shouldn't be a big surprise to us because we know the original function that we were looking at was a linear function. 3x minus 2 is linear. And it happens to have a slope value of 3. So this is actually what we're trying to find, is the derivative gives me the slope at any one input of the function. So this gives me f prime of x. This is the rate of change, or the really the instantaneous rate of change at any one point on the domain of the function. And so in this case, that would just be that slope value because we have a linear function to begin with. The secondary question we want to answer is the f prime of 5. So if I know f prime of x is constant, we know f prime of 5, well, that would also have to be constant at 3. It doesn't matter what point in the function I'm at, I'm always going to have a slope of 3, or a rate of change of 3 at any one point for the f function. Let's take a look at the second question. We want to go ahead and try to use our second definition here, the definition of the derivative at a single point, to evaluate what is g prime of 2 in our second example. So we'll take a look at g of x is equal to negative 5x squared plus 7x, and we want to use the definition of the derivative at a point to find g prime of 2. So here we're going to be solving for here g prime of 2, and again here that means a, that value is going to be 2. We're going to fill in the point that we're interested in. So a in this equation has to be 2. So by definition, we would write out this as the limit as h goes to 0 of, this is going to be g of 2 plus h minus g of 2 over h. So there's a couple items that I'd like to go out and find. First, what is g of 2 plus h? We'll do that on the side. And then we also want g of 2. So let's try the g of 2 plus h. We'll evaluate our function. This is negative 5 times 2 plus h, quantity squared, plus 7 times 2 plus h. And then we can do some simplification before we put it back inside the limit. So we have negative 5. If we square this out, 2 plus h, we can consider a binomial product here. Squaring the first gives us 4, plus 2 times the product would be 2 times 2 times h, or 4h, and then plus h squared. And then a final distribution here, 7 and 2 and 7 and h, give me 14. And then plus 7h. And we have a little bit more distribution we could do with that negative 5, so let's do that before we move on. We have negative 5 and 4. We get negative 20h and negative 5h squared, plus 14, and then plus 7h. It doesn't appear that we have any like terms to go ahead and simplify there, so we'll just kind of leave that as it is for right now. And we'll go ahead and try to find what is g of 2. This is just the regular functional value at 2. So we'll evaluate this at negative 5. We'll have 2 squared, and then plus 7 times 2. So it looks like we'll have negative 5 and 4, that's negative 20, plus a 14 is equal to negative 6. So we have a negative 6 there for our final result for that functional value. And we're going to go ahead and fill that in. So we have the limit as h goes to 0. We're going to fill in those numerator terms as they sit. So this takes a look at the following. We have negative 20 minus 20h minus 5h squared plus 14, and plus 7h, and it does look like we do have a like term to work with there. Oops, we should have a plus 14 and plus 7h, and then we're going to subtract 6 because, or subtract a negative 6 there because that's my g of 2. So subtracting negative 6 is my g of 2, and then divide by h. So let's maybe highlight those like terms that I just noticed. We have negative 20, 14, and then here we'll have a plus 6 that'll pop up. So if we add all those together, I believe that's just going to cancel out to 0. So those all together, those constants go to 0. So let's go ahead and write the limit one more time before we do cancellations. We have negative 20h. We have minus 5h squared. And looks like we do have another like term there we can fix up here. So let me do that with another color. We have negative 20h and then 7h. That gives us negative 13h. So let's rewrite the limit with that. And then we'll have the minus 5h squared. So we have the limit as h goes to 0. We'll have negative 13h minus 5h squared, and then divided by h. So that's nice and simplified there for us. Now we can see to dividing out an h for these terms. Each of them have one h, so we can get rid of 1, and then we will look like to be able to evaluate this limit as h goes to 0. We have negative 13, that's a constant, minus 5h. And so if I evaluate my limit now, I'm kind of safe to do that. As h goes to 0, this term will go to 0. And so we'll be left with that constant negative 13 for that limit. And therefore, that's going to be our derivative at g prime of 2. So at 2, the derivative at 2 is going to be negative 13. All right. So we might want to consider maybe a pattern or something that we could take from this. The second problem, since we're doing it at a point, we don't necessarily see the general derivative from that second example, but we can maybe take off maybe a little pattern from our first one, just to look. Notice that we go from a linear function to a constant function when we take its derivative. So whenever we have linear functions, their derivatives is always going to be the same as the slope of that line. As we go to take a look at the next couple of rules here, we'll see kind of some patterns dealing with the powers of the function. We're going to consider the power rule next in our derivative rules. And we'll try to get to a number of different rules as we go along in these sections. So how we're going to approach derivative rules here is we're going to just take them in sections here. The first 4 rules we have below, and we'll try to get through these rules first. So these 4 rules you'll use quite a bit throughout every problem, so that's why I want to kind of address these first. So the first rule that we'll come across here for the derivatives is the constant rule. So this tells us that any constant value, its derivative is going to be 0. The constant multiplier rule, if we have a function or power term multiplied by some constant value, that constant multiple stays in the derivative, and we take the derivative of the function of x that it's attached to. The power rule is a really important rule that we'll want to know. And that takes a function of the form x to the n power, where n is a constant value. This could be positive or negative. And we would take the derivative by multiplying by the exponent and subtracting the exponent by 1. So the derivative of x to the n becomes n times x minus 1. Or n times x to the n minus 1. And then another rule that we can consider is the sum and difference rule. If we have individual terms that we're taking a derivative of, say an f function, a g function added or subtracted together, we can take their individual derivatives and then add or subtract them together. That would be the sum and difference rule. So let's consider kind of all of these rules will be kind of in this function here. We have the f function in part A is 4x squared plus 7x minus 3. So if I considered this to start out, my notation here would be, again, f prime of x as its derivative is equal to, I'm going to take it term by term, we have 4x squared. So the constant multiplier rule tells us that we can keep the constant multiple, 4, inside the derivative term. And then I'm going to take the derivative of the function of x. That would be take down the power, that's 2, and then raise x to the 2 minus 1. That would be the power rule, and then the constant multiplier rule. And I'll simplify this in just a little bit as we go through each term. If I take a look at the next term, I'm going to add, the constant multiple is 7, and the derivative of x itself is really, you could write it like this, 1x to the 0 power, because that's 1 minus 1. Now, usually we wouldn't write it like that. It would just be x to the 0, which is 1. So whenever we have a linear term like this, the derivative is simply just going to be that constant. And then the last term there, if we take the derivative of negative 3, well, that means we're taking the derivative, and the constant rule comes into play, and that's just going to be 0. So if I summarize this derivative and write it a little bit better, we have 4 times 2 is 8, x to the first power. And then the second term would just become plus 7. 1 times x to the 0 power is still 1. And so we'd have 7, and then 0 does not get to come along. So this derivative here would be just 8x plus 7. If we take a look at the next function, this is a g of x function. Let's go ahead and go term by term with this one as well. G prime of x would be the derivative name. We could keep the constant multiple in the first term as negative 7, and then the derivative of 4 to the x we would call 4x to the third power. We bring down the power and subtract 1 from the exponent. We've seen a linear term like this in the previous step, so the derivative of negative 6x would be just negative 6x to the 0. So that would be just negative 6, just going to be a constant. Now the last term we have is a little tricky because we have to work with this in the numerator. So if I need to get these powers in the numerator, one way I could rewrite this term is x to the negative second power. And we can still use the power rule with negative exponents. So let's apply the power rule here to x to the negative 2. That would be bring down my power, negative 2, raise x to the power minus 1. So that would be negative third power. So the derivative of 1 over x squared there would be 2x to the negative third. Now we can clean this up just a little bit. G prime of x is going to be negative 28 x cubed. minus 6, and then minus, we'll have 2 divided by, we can put this back in the denominator as a positive power of x, so negative 2x cubed. And that would be our final derivative there. The next value we'll have is for c, h of x. This one looks like it has some different looking powers here with some fractions and square roots. So before I go, let me just rewrite this. We're going to want to find, again, h prime of x. And if I consider the square root of x in this first term, another way I could write that is 2x raised to the 1/2 power. And we'll want to convert those square roots or cube roots that we have as powers of x as rational exponents to be able to use the power rule. So let's apply the power rule in that first term. That constant multiple would be 2. We'd bring down the 1/2 and then raise x to the negative 1/2 because we're subtracting 1 from the power. So that's our first term. The second term, we have negative 4 is the constant multiple. We'll keep that. We'll bring down the power 2/3 and raise x to the 2/3 minus 1. That's negative 1/3. Now, the last term here, negative e, well, e as a value is just a constant number. So we want to be careful here. This is not e to the x like an exponential. This is simply just e. And so this value here is constant. So we want to treat it like a constant when we take the derivative. So its derivative there would be, if we wanted to write it, minus 0 or plus 0, regardless. It's going to be 0 either way. We'll take a look at exponential derivatives as well. And those will have a derivative other than 0. But this is just its constant base e. So that's just a constant value. So let's rewrite this one more time so it's nice and clean. We'd have 2 and 1/2 give me 1. And then the x to the negative 1/2 we could rewrite as a square root of x, but that would be in the denominator. So we can rewrite that as 1 times 1 over x squared, or 1 over the square root of x. And that's where we could leave it. We can do the second one, multiply our constant with 2. That would be 8/3. And then this would be a cube root in the denominator for x to the negative 1/3. So that would be 3, then cube roots of x. And since we don't have to add in that 0, we will be satisfied with that. We'll keep that as our derivative. In the next video, we will jump into a few more rules. We'll look at the product rule, quotient rule, and then we'll look at exponentials and logs as well. So thanks for watching. I look forward to seeing you in the next video.